All right, ladies and gents, cool and interesting thing. We've been talking so far about these different spectra. There are actually 3 different types, and you need to know which is which. If you have something that is a hot solid or the body of a star, it is going to give you the continuous spectrum. And a continuous spectrum looks like this. All of the colors of the rainbow, there are no gaps in it. If you have a hot gas, that hot gas is going to produce an emission spectra. Each one of these lines corresponds to a unique electron jump inside of that element. And this is, as I mentioned, like the fingerprint of that element or chemical. Stars, on the other hand, don't give us continuous spectra, do not give us emission spectra. They give us something which is called an absorption spectra. The absorption spectra is kind of like continuous and emission merged, and that's actually how absorption spectra get produced. An absorption spectra is all of the colors of the rainbow with black lines in the place of the bright lines in an emission spectra. So how do these get produced? Well, it kind of works like this. Let's say that you had a hot star or a hot dense solid. It's going to give you the full rainbow. But stars are big balls of gas, and the middle is going to be a hot plasma that is so dense that it produces this continuous spectra. But around the outside layer, there is actually a gaseous layer. This is the corona of our sun. It's only visible during a solar eclipse, and that is a big layer of gas. Gases produce emission spectra. So these two come together and give us this absorption spectra, where there are black lines in exactly the same places where these bright lines are. So how does this occur? Because what was here actually goes missing. Well, how the heck does it go missing? Well, here's how this works. The body of the star is going to produce that full spectra. The gas has electrons in it and chemicals in it with energy levels. So it's just sitting here minding its own business in a gas, and all of a sudden this bright white light goes past it. And as that white light goes past it, the element can absorb only specific wavelengths of light. And if the element happens to be hydrogen, it's going to absorb some reds, some blues, some purples, but not every color in the rainbow. So the gases in that outer corona, that outside layer of gas, are going to actually absorb, kind of like a sponge, the specific wavelengths that correspond to its elements in that gas. So it basically takes out the colors from the full rainbow. And that's how you get this absorption spectra. And that's actually what comes to our eyes back here on Earth. This is one of my absolute favorite pictures. This is the complete spectra of our sun. We have a tendency to think that our sun is shining down on us all of the colors of the rainbow. That's not true. There are many, many, many wavelengths of light that are actually missing. And astronomers and scientists who look at something like this can tell so much more than just the elements that make up the sun. They can also tell relative abundance. Here's how you can determine that relative abundance. I need a nice dark pen for this. Now take a look at this line and this line. Aren't those nice and dark and rich? Here's another. Look at those 3 lines, really dark, strong lines. When this spectra gets analyzed, wherever there's big, strong lines, that means there's a high percentage of those chemicals in that star. If you go to an area like right in here, those lines are kind of wimpy, really wimpy. Well, that indicates that you have a low percentage of those elements. Today we use computers to help do this spectral analysis, but the brightness of the lines, the distribution of the lines can tell us chemical composition and percentage of each. Now, the first gentleman who actually figured this out to some extent was a gentleman named William Fraunhofer about 200 years ago. Fraunhofer is the first person who actually carefully looked at the sun's spectrum, and he noticed these gaps or these black lines. To this day, these black lines in the solar spectra are called Fraunhofer lines, and you need to know his name, and you need to know that definition, that he's the fellow, he found those dark lines, and that the dark lines in the solar spectrum are known as Fraunhofer lines. Here's an absolutely stunning picture. This is a reproduction of Fraunhofer's original drawing, and it may not look like anything, but this was 200 years ago, and for 200 years ago, great detail. Each one of these little black lines are precisely placed, and they are a clue and an indicator of chemical composition of the stars. The most abundant element in the universe is hydrogen. And because of that, and the fact that hydrogen is so abundant in stars, the unique lines in the hydrogen spectra actually have their own name. The visible part of the hydrogen spectra is called the Balmer series because of the gentleman who carefully analyzed it. And each line are called the hydrogen alpha, beta, gamma, and delta. This is like A, B, C, and D in Greek. And those lines are specifically named for those emission and absorption lines. We know not only the visible fraction of the hydrogen spectra, we've also analyzed the portion of the hydrogen spectra that's in the ultraviolet, so your human eye cannot catch them or pick them up. There's also the infrared portion of the hydrogen spectra. And astronomers are going to analyze every bit of data that they can get their hands on, and that is going to include all fractions of this. When you become a big hotsy-totsy astronomer, you are going to see pictures that look more like this. Now, this is the absorption spectra of a star, coupled with, do you see this kind of a shape? This relates back to that black body curve that we were talking about earlier in this chapter. And the black body curve where that peaks is a big indicator of the temperature of the star. And then those rough up and down sections, those correspond to, like here it says sodium. Well, there's a darker line. Here's the hydrogen beta line. And there, see that dark line there? By analyzing this, this is how astronomers can tell the temperature and the chemical composition of each unique star. We'll see you next time. Bye-bye.